So how a gravitometer works is very simple. It's pretty much a box with a spring and a mass inside of it. And obviously, if it's over a body with a higher density, they exert a force on each other, so it pulls towards. And so you're measuring that change in the spring. But you can't just have a spring just hanging around. It actually gets locked in place when you're transporting the gravitometer. The other thing is some springs over time, if you see them, they stretch and they get extended. So the temperature of the spring is important because it can actually affect the length of the spring. So in the gravitometer, there's actually a heater that keeps it at a constant temperature. But we did speak about the fact that the gravitometer, every 2 or 3 hours, you have to go back to your base station and make a measurement there. And the reason is to compare the two measurements, because I'm going to the exact same space, the reading should be exactly the same, but what you often find is that the reading increases over time, and that's because of this drift. And it's because of a slow extension of the spring. So even though you've got a heater in there, even though you've got a fancy spring, you can't avoid it. So therefore, you've got to be careful with your measurements. And so then something that we do very often is a microgravity survey, which you might hear about. And it's when you want to measure small changes in gravity. We've already spoken about small changes. This is even smaller changes in gravity. And so they say, for example, if you're trying to find mine workings or caves or environmental. So what Sue Webb, who you met, she did a microgravity survey up in the Magaliesberg. They were looking for water. And so they were looking where the water went, where the aquifer was that the water was in. And so they did a gravity survey in spring, and then they came back and did it again in autumn, because there was going to be slight changes because the water was going to have drained out. And so that's a microgravity survey, very, very accurate. So you can see these values are, we were looking at accuracies of 0.04, so this is looking even smaller. You also have very small station spacing. So on field school, you usually have spacings of about 20 meters. Now it's down to 1 to 5 meters. So these would be quite expensive surveys, but it's over a smaller area. And the height measurement, so with your GPS, have to be extremely accurate. So centimeter to millimeter level. So you can't use a handheld GPS, which is like 5 meter accuracy. You've got to use the special GPS, and you would repeat the measurements yearly. Okay, so now we can do our question. So it says you've got an ancient burial chamber is trying to be found using a microgravity survey. The chamber is likely to be 4 meters across with a covering of up to 3 meters and material density of 2,000 kilograms per meter cube. Estimate the magnitude of the anomaly and a suitable grid spacing. So this is going to take into account the fact, remember the other day we were talking about the Nyquist frequency. So that was how often you needed to sample your anomaly so that you could see the actual anomaly. So a background picture, just so that we're all on the same page calculating it. So we've got a surface at 0 meters, we've got a chamber about 4 meters across, and so it says with a covering of up to 3 meters. So previously we've been doing from the surface to the center. That's not a covering. A covering is on top of the body. So on top of the body is 3 meters. So that means to the center of the body is going to be 7 meters, if I'm making a measurement here. And it's always to the center of the body. The material on the outside has got a density of about 2,000 kilograms per meters cubed. And so that tells me this is most likely sedimentary rock. Not that you need to know, but that's also, you don't usually find caves in igneous rocks. You find caves in like limestone, rocks that can be weathered very easily. So calculate the magnitude of your anomaly. Remember that your x values are going to be increasing from 0, they go positive that way and negative that way. And so are you expecting a positive anomaly or a negative anomaly? Because it's a chamber, so it's most likely got air inside. And the air, it's easy, it's up there. Density of air is equal to 1.225 kilograms per meter cube. So negative or positive? Negative, yeah. So, and it's quite a big difference. You can see this density contrast is like 1,999. Okay, do you want to give it a try in Excel? So exactly what we were doing the other day, and then plot up the curve, and then we can talk about this final question of what is a suitable grid space.
So once you've done it in Excel, you should get a plot that looks something like this.
Tell me how often we should take a measurement when we're doing our gravity survey. You can use the equations that we spoke about in class, but I want you to just give me your gut feel. Where would you take a measurement? You also want to get to the background values. You want to know that it's to 0. So I can only afford 5 or less measurements. Okay, so you're literally 30. You're still getting an idea of how big the anomaly is. You're losing a lot of information about how like the shape of it. So it's going to be more difficult to define your anomaly. But if you don't have money and that's all you can do, then that's all you can do. I mean, I'd say if you could just do 3, then maybe do 40, 0, and minus 40. Those are the only 3 you can do. I would don't do minus 10, 0, minus 10, just because then you have no idea when it gets to 0. You need to know how it's getting to 0.